Good evening, everyone. Welcome to the fifth live session for the course Concrete Technology offered by NPTEL. I am Harshit Agrawal, a PMRF scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for the entire course duration. So, in today's session, we'll first revisit the last live session that was for week 4 content in a quick recap manner, and then we'll look into things that were covered in the week 5 content. The week 5 content that we'll discuss today is about mixture design of concrete, which is divided into following subsections for today's discussion. So we'll start with an overview of mixture design. Then we'll discuss about target mean strength and characteristic compressive strength. We'll discuss about IS 456 and IS 10262 based mixture design of concrete. And finally, we'll talk about DOE method of mixture design. In between, I will have some theoretical and some numerical questions also related to the mixture design concept. Around 11 questions it will be there in total. And finally, we'll conclude the discussion and I will try to address any other queries post discussion. So last week we concluded the fourth week of the course where we talked about chemical and mineral admixture used in concreting. First discussed about chemical admixtures used in concreting. So basically chemical admixtures are products which are added in very small quantity during mixing of concrete, and they aim to modify the fresh state behavior of concrete. So in this, we classified chemical admixtures into different categories. We talked about dispersion admixtures, which adsorb on cement surface to cause particle dispersion, which included plasticizers and superplasticizers. We talked about admixtures which interact in hydration, that those are accelerators and retarders. We talked about air entraining admixtures that are used basically in to resist the freeze thaw action. We talked about viscosity modifiers, and we just touched up a little bit upon special chemicals that are used in concrete like corrosion inhibitors and water repellent admixtures. Then we discussed in detail about plasticizers and superplasticizers, where what are they, their chemical composition and how they cause dispersion in concrete, either via steric hindrance between hydrophilic groups or due to electrostatic repulsion between cement grains with high zeta potential. At the end, we saw what all domains of application a water reducing admixture has, either strength increase or workability increase or cost decrease. Then we discussed about accelerators and retarders. We discussed how they interact with cement hydration and affect setting of cement paste by affecting the rate of dissolution of different ionic species. Retarders enhance the effect of gypsum to delay the C3A reaction with water, or delay the dissolution of calcium ions to delay formation of hydration product, whereas accelerator on the other hand does the opposite of what retarder does. Then we discussed about air entraining admixtures and viscosity modifying admixtures, and particularly paid attention where they are used. So air entraining admixture are important in cold weather concreting where freeze and thaw action is a major durability issue, while viscosity modifying admixtures are used in self-compacting concrete to control segregation and bleeding issues with concrete. Then we started discussion on mineral admixture, also known as supplementary cementitious materials. Those are used as a partial replacement of cement to promote sustainability and to improve strength and durability. We saw production of some of the commonly used SCMs like fly ash, ground granulated blast furnace slag, and silica fume. We talked about characterization of SCMs to understand why SCMs are reactive and how they differ from each other. We saw different testing methods to evaluate reactivity of a mineral admixture, which are pozzolanic activity index testing and lime reactivity testing. We talked about hydration of pozzolana and pozzolanic reaction. We talked about effect of mineral admixture on fresh properties like setting time. So we discussed that fly ash due to their ball bearing effect delays setting, while silica fume due to its high surface area accelerates the setting. The same reason applies for water demand and SP demand also, where fly ash will reduce water demand and SP demand, while silica fume will increase water and SP demand. In terms of hardened property, we saw that fly ash and slag due to their slow reactivity shows slower initial strength gain, but after a prolonged age they will have a higher strength, while silica fume from early ages only show higher strength. In trying shrinkage and creep, we discussed fly ash and slag shows lower shrinkage, while silica fume shows higher shrinkage risk, and all three admixtures they reduce creep. And finally, we discussed about how durability properties are affected due to SCMs, where due to pore densification, all SCMs they will reduce the rate of chloride diffusion after prolonged hydration ages. However, in terms of carbonation induced corrosion due to consumption of calcium hydroxide by secondary supplementary reaction by SCMs, they increase the carbonation depth. So it is a mixed effect. They are delaying the permeability of CO2, but at the same time they have also consumed CH which reacts with CO2. Okay, so this was all from last discussion. Does anyone has any doubt in the discussion? Okay, if there are no doubts in the last session, we will move to the today's session. Now, in week 5, we have started with the mixture design of concrete. So, we all know concrete is a heterogeneous mixture comprising of various components as listed in this equation, and this equation we have seen in the first live session. Till date, till week 4 content, we have talked about each of these components separately. Now it is the time to see them as a mixture in concrete, and for today's session the aim is to understand how they are proportioned to make concrete. So first of all, what do we mean by when we say mixture design of concrete? So mixture design is a process of determining proportions of various components that are needed to be combined to create a concrete mix with desired properties. Now, here we have used the term desired properties. So what do we mean by desired properties? So there are different factors that determine a property of concrete like strength, workability, durability, appearance, and use of any specific material in concrete. All of them dictate the properties that we need from concrete, and thus it controls the mixture design of concrete. Like, suppose for a M30 grade concrete and for a M50 grade concrete, my mixture design will be different. Likewise, for a 50 slump and for a 150 slump, my mixture design will be different. Other examples can be a concrete which just uses OPC and a concrete which uses OPC plus fly ash or silica fume. Again, my mixture design will be different. So, several factors or several desired properties can govern the mixture design of a concrete. Now, why this is important, why we do mixture design of concrete? So, this is important to create a concrete mix which is cost effective, easy to place, compact, and meets all performance requirement. And this you can again understand from the same set of example I talked right now. M30 grade, M50 grade, high slump, low slump. These are all properties that we want from concrete. So for achieving those properties, we need to do proper mixture design so that we can achieve those properties. Now, there are vast number of components that are involved in concrete mixture design. Some of them are cement grade, so it can be OPC 33 grade, OPC 43 grade, OPC 53 grade. Then aggregate size and shape, there can be rounded aggregates or angular aggregates. There can be 10 passing aggregate, 20 passing aggregates. Aggregate grading zone, for fine aggregates, they can belong to zone 1, 2, 3, 4. Then specific gravity of constituent materials used in concrete like OPC, aggregate, fine aggregate, fly ash, or any chemical admixtures which is used. Water absorption capacities of aggregate, which will help us to keep our W by C ratio same as desired and take extra water that is absorbed by aggregate into account. Then type and amount of admixtures that we are adding like super plasticizers, retarders, accelerators. Slump that we demand from concrete, like 50 slump we want, or 100 or 150 how much flowable we want our concrete mixture to be. And finally, the most important factor is the water to cement ratio, which plays a important role in governing the strength and the durability of concrete. So these all listed factors, they are fine tuned. and designed to contribute to the ultimate product, which is concrete, to achieve a specific performance demand from concrete. Now, the choice and the proportioning of these components, they depend on what properties we want from concrete. So in fresh state, properties we refer by workability and handling properties of concrete before it sets, and fresh state we express in terms of slump value. In hardened state, we define performance of concrete after it has set and gained strength, and we represent hardened state properties by compressive strength. And in durability properties, we refer to the ability of concrete to resist any environmental action or environmental attack over time. And these are expressed by applying control over design parameters like water and cement content. Okay, so each set of properties that we want from concrete is desired in terms of a strength indicator or a representation. Okay. Now, each component that is added into concrete can affect one or more desired properties from concrete. Like fresh properties is dependent upon water content, grading of aggregates, and shape of aggregates. How? Higher water content will increase the flowability of concrete. Proper grading of aggregate ensures high packing density, and thus, with the limited cement paste, we can have higher workability in concrete, as we discussed in week 2 content. And shape of aggregates like ground aggregates have lower interlocking and frictional resistance, so they can promote more workability in fresh state. Hardened state is mainly affected by binder content, binder composition, and W by C ratio. How? Higher binder content will increase the compressive strength. By binder here we mean OPC with or without mineral admixture. Okay. Then binder composition, if we have silica fume or any other SCM in my composition as a replacement of OPC, then they can affect the short term and long term strength. And W by C ratio, which we know it is inversely proportional to strength. So if I represent compressive strength on y-axis and W by C ratio on x-axis, then they follow a exponential relationship. Okay, so as my W by C ratio increases, my compressive strength decreases. Then durability properties is mainly affected by water to cement ratio and cement content. How? So water to cement or water to binder ratio, as it increases, my porosity in concrete increases. So ions will easily penetrate inside concrete and they can cause durability issues in concrete. Similarly, higher binder content means denser concrete and thus lower permeability of concrete, so better durability performance of concrete. Okay, so in this way, different components that we add in concrete, they can affect different properties that we want for from concrete. Okay, so to make a mixture using different individual component, there can be different approach a person can opt for. Like one may go for proportioning using trial mix. For example, suppose a contractor wants to design a M30 grade concrete. So in a trial mix, he will choose some cement, water and aggregate ratio and he will prepare concrete, and after 28 days, he will check the strength of concrete. If the strength is passing the M30 grade criteria, then the proportioning is okay. If it is not passing the criteria, then he will change the proportioning and he will again do the strength trial, and this will continue to go on until he gets the perfect mixture. So this is trial mix approach. Second is empirical method, which is based on experience. So as you will prepare more and more concrete mixtures, after some time you will get an idea how you will get an idea from your experience what proportion to use to achieve a certain grade or a certain fresh property. But this comes out accurate only after you have gained sufficient experience in mixture design. And the third is based on recommendations from relevant mixture design standards. So there are several standards that have been made to aid the mixture design of concrete. Like there are Indian Standard Method IS 456 and IS 10262. There is DOE method, there is ACI method, and there is BS method, British Standard for Mixture Design. So when we follow instructions and steps in these design guidelines, we can achieve a desired concrete mixture for our desired need. Now, in all forms of mixture design that we are discussing here, One parameter which holds the center stage in proportioning is the characteristic compressive strength and the target mean strength that we want from concrete. So first of all, if you see a graph here, the x-axis represents the compressive strength and y-axis represents the frequency, like the number of times a certain strength value was recorded. Suppose you have done 100 tests on a concrete cube. So for 100 tests, I will get 100 results. So it will represent the frequency, like how many times 25 MPa strength came, how many times 28 MPa strength came. So that represents the frequency of repetition of a certain strength value. Okay, so when a mixture design is done, different concrete assemblies are prepared, like cubes and cylinders. Now, not all assemblies will have the exact same strength. In some cases, there will be like when I'm pouring concrete into molds, in some cases, what will happen? There will be lesser paste or more aggregates, or void percent can vary from one cube to another, or maybe two mixtures are prepared with the exact same proportion, but they can still vary in their properties by a bit. Okay, so suppose a person prepares 30 concrete cubes. When he does the compressor strength test on those 30 cubes, he will get a curve like this. Okay, with varying strength. Okay, such distribution of strength is known as normal distribution. Okay, so there is higher proportion of strength to come near mean, the one which we wanted to design, but there will be standard deviation across mean also in few samples. Okay, so how we calculate the mean? By by simply summing all the compressive strength value and dividing by the number of observation. Okay, so if there are 30 observation, then we will add strength of all 30 observation and we will divide by 30. So this will give me the mean strength, the target mean strength from the concrete. And how to calculate the deviation from mean? So that deviation from mean is known as standard deviation, and it is calculated using this formula. So we have compressive strength values of 30 samples. We know the mean strength. So compressive strength minus mean strength square, sum of all the values divided by n minus 1. Okay, so this will give me the s square value, and s is my standard deviation. So in this way I will know how much deviation is there across mean. If my concreting is not proper, or if I don't have much control over my concreting, then standard deviation will be high. If I have very proper control over concreting, where each cube is has almost same proportion of all the components, then my standard deviation also will be very low. Okay, so this standard deviation, it defines the precision, how much strength is deviating from mean. So whenever we represent concrete, okay, we need both the data, mean and standard deviation. Now whenever we represent a concrete, you have seen that we say M30, M40, M50 like this. So here 30, 40, 50, these are known as the characteristic compressive strength of concrete in megapascal. Okay, and what is characteristic compressive strength? So suppose I have done 100 trials of concrete strength, then characteristic compressive strength will the value which is above which 95 samples lie. So we say that characteristic compressive strength is that strength below which no more than 5% of the samples will lie. Okay, now there will be two questions in your mind. First is why 5%? And second, as we told few slides back, after 28 days we record the characteristic compressive strength. Then now why 28 days and why 5%? So 28 days, it is because it is observed for OPC based concrete, after 28 days almost 99% of strength gain happens. Okay, after 28 days. So that's why whenever we cast a concrete batch, after 28 days we check the strength of that concrete, and that strength we represent as characteristic compressive strength of concrete. And why 5%? So this is something which was fixed over n number of repetition as a statistical representation of safety factor. Okay, like suppose you did strength testing on 100 cubes for M30 grade. So 95 cubes will have a strength of more than 30 MPa at 28 days. Okay, so this is a representative strength. However, when we do mixture design, we use target mean strength for designing. Okay, so if I know the characteristic compressive strength that I want from concrete at 28 days, then this plus 1.65 times the standard deviation value will give me the target mean strength. So whenever we do design, we design for target mean strength, and whenever we check the concrete quality, we check for characteristic compressive strength. Okay, so we design for target mean strength and we represent in terms of FCK, characteristic compressive strength. Okay. Now just try to answer these three simple questions based on the theoretical part of mixture design. And in the meantime, if you have any doubt regarding whatever we have discussed till now, you can ask. Generally, silica fume is much finer. It is like among all SCMs, silica fume is much finer than other SCMs. Like OPC has a fineness, silica fume is almost 10 to 15 times finer than OPC. Rice husk ash may be like two times finer or three times finer. I don't have much idea about specific surface area, but for silica fume, it is very fine. The most reactive SCM among all. Try to answer all the three questions. Question number one: which of the following is the most critical factor in determining the ultimate strength of concrete? Can anyone tell me? I have received only one answer. Others also give it a try. Yes, the correct answer is B. So we have seen water to cement ratio. It is inversely proportional to the strength of concrete. Okay, and it is the most critical parameter for determining the ultimate strength of concrete. Question number two: which of the following is not considered when determining the target mean strength in the concrete mixture design? Can anyone tell me the answer for question number two? Yes, the correct answer is C, because temperature fluctuation, it is very difficult to take into account. Required strength, so we have seen required characteristic strength and standard deviation, they both combine to define the target mean strength, and degree of quality control at site is also very important. So if quality control is low, standard deviation will be high. So target mean strength will be more than what is required. So suppose I want to cast a concrete of FCK value of 30 MPa. But if I know my quality control at site is poor, then I need to at least cast for 35 or 40 MPa so that 95% of my sample will be above 30 MPa. So that's why degree of quality control at site is also important in determining the target mean strength. Question number three: which of the following changes in the mix design is likely to increase the bleeding in fresh concrete? It should be mixture design. Which of the following changes in the mixture design is likely to increase the bleeding in fresh concrete? So the correct answer is D, using high slump mix. So high slump means more flowable concrete, okay, for which one may use super plasticizer. And if the dosage of super plasticizer is more than required, then there can be bleeding in concrete. Okay, so that's why we have said last in the last session, dosage of chemical admixtures are very sensitive. If they we go beyond a certain limit, then it can ruin the entire concrete mixture. Now try to answer these three more questions related to mixture design basics. Question number 4. Why is lower W by C ratio preferred for high strength concrete? So we have seen W by C ratio and strength have an inverse relationship. Why is there an inverse relationship? And why we prefer lower W by C ratio for high strength concrete? Yes, the correct answer is B. So when we have a low W by C ratio, then the porosity inside concrete is also low. This means that the amount of water filled voids inside concrete is low, and thus shrinkage issues will be lower, and permeability of concrete will also be lower. Okay, so W by C ratio as it decreases, the porosity inside concrete decreases, and that's why strength increases. And as porosity decreases, all the durability issues will also decrease. Which of the following is not a commonly used method for improving workability in a concrete mix design? So, which method we don't use to improve workability? For question number 5, the correct answer is C. Okay, so if we are increasing cement content, we are reducing the W by C ratio. Now, if we are reducing the W by C ratio, we won't be improving the workability. We will do the opposite. Okay, because now there is less free water available in concrete, so it will make concrete stiffer rather than flowable. Question number 6. For a given concrete mixture, which condition would likely require an increase in air entraining admixture dosage? So when I will require air entraining admixture, if I am doing concreting in cold weather, so which mixture for which component will make me require increased dosage of air entraining admixture? No, increased lump requirement is not the right answer. We are introducing air voids inside concrete when we are adding more air entraining admixtures. Okay, so the correct answer for this will be B, higher fineness modulus of sand. How? Because higher fineness modulus means coarser sand, okay, which will reduce the air content in the concrete mixture. Okay, so we'll have to add more air entering admixture to to maintain the desired air voids that we need from concrete. Okay, it should be lower fineness modulus. It is my mistake. Lower fineness modulus of sand means that it is coarser sand. Okay. Okay. So let's move ahead to the next part of the session. Okay. So we have understood the basis of mixture design, like why we need mixture design. okay, and how we do mixture design, overview of how we do mixture design. Now we'll start discussing mixture design as per Indian standard guidelines. Now here, though I am covering the standards, it is important for everyone to read the standards on their own also once, line by line, because it that is the best way to learn the codal provision. Okay, I today I am giving just an overview of what is there in both the standard IS 456 and IS 10262. But if you will read by your own, you will get a much better clarity about each clause that is present in the standard. Okay, so for mixture design, there are two important Indian standards. First is IS 456 and the other is IS 10262. So IS 456, which is Indian Standard Code for Plain and Reinforced Concrete, it provides guideline for concrete mixture proportioning to achieve desired strength, durability, and workability. So there and IS 10262 is uh, is the one which provides the detailed procedure for doing mixture design in concrete. Okay, IS 456, it just provides general principles and requirement, but how to apply those principles, how to mix different components in a proportion, everything is provided by IS 10262. Okay, so there are several key points in IS 456 which is related to mixture design. Okay, first of them is type of concrete mixture. Okay, so first we'll discuss about IS 456 and then we'll discuss about IS 10262. So in IS 456, the first key point which is there, it is the type of concrete mixture. So as per Indian standard, concrete mixture is two has two broad classification. One is the nominal mixture concrete, nominal mixed concrete, and second is the design mixed concrete. So nominal mixed concrete includes simplified proportion of mixture proportion. Okay, so in this we represent mixture proportion as a ratio of three numbers. 1 is to 2 is to 3, or 1 is to 1 is to 2. So one represents water, for one of them will represent water, one of them will represent cement, and the third one will represent aggregate. Okay, so in this way we do nominal mix, we represent mixture in terms of proportion, and this is used for low strength concrete like M10, M15, and M20 grade. Whereas design mix concrete is where we engineer the proportion of individual components through laboratory trials for a specific strength and durability requirement, and these are used for concrete having strength greater than M55 grade and above. Okay, so if you see in IS 456 table 2, concrete is divided into three groups: ordinary concrete, standard concrete, and high strength concrete. So ordinary concrete has these three grades: M10, M15, and M20, for which we opt for nominal mix design. So um, and standard concrete goes from M25 to M55, and high strength concrete goes from M60 to M80. So here if you read the first point below, okay, so this 25, 35, 55, all these are the compressive strength of 150 size cube, 150 size cube at 28 days. Okay, so code has even mentioned what size cube we need to test and at what age to check the grade of concrete. And the second point below you can see says that high strength concrete, that is above M60 and above, they need to be designed based on the proportions that are present in past literature, that is like previously published article where high strength concrete was prepared, and from experimental trials. So when we talk about mixture design code, that is IS 10262, that we mainly use for standard grade concrete from M25 to M55. Okay, now for nominal mixture design we have table 9 which is there in IS 456. And here for specific low grade concrete, the quantities of total aggregate per 50 kg of cement, the ratio of coarse to fine aggregate, and the amount of water to be taken is mentioned. So you can see here there are different grades of concrete from M5 to M20. Now total quantity of dry aggregate that should be added per 50 kg of cement, it is mentioned. So this is 800 kg, 625 kg, 480 kg, 330 kg, and 250 kg. So this is the total quantity of dry aggregate. This includes both fine aggregate and coarse aggregate. Then The proportion of fine to coarse aggregate is also given, that is usually 1 is to 2, but it can be between 1 is to 1.5 and 1 is to 2, 2.5. And quantity of water to be added is also mentioned. Okay, so for a specific cement quantity, we know the aggregate quantity, we know the aggregate proportion, and we know the water quantity. So that's why we say it is a proportional based mixture design, and that we opt for nominal mixture, that we offer low grade concrete. However, in reality, nowadays a concrete of strength below M25 is rarely used. So this table won't my you won't find much use in practice. Then the second key point of IS 456 is mixture proportioning, which is influenced by four key parameters. First is the W by C ratio. So it should be capped as low as possible for strength and durability. And maximum W by C ratio for different exposure condition is specified in IS 456. So this will see after few slides. Then cement content, again minimum cement content is specified for different environmental condition. Again this point we'll see later on. Aggregates. So selection of aggregates, fine and coarse aggregate is based on grading, shape, and strength. So this thing also you will see when we will discuss in detail about mixture design today. And admixtures. So admixtures like fly ash, GGBFS, plasticizers, and retardants can be used for improving workability and performance. That is what IS 456 code is saying. The third point is the target mean strength. So whatever concrete we prepare, it is for achieving a certain target mean strength when we know the characteristic compressive strength that is required. So simply saying, we know the FCK value and we design for FCM, target mean strength. Okay. Fourth point is workability. So workability depends on the placement method, reinforcement congestion, and environmental condition. Okay, so how much flowable we want our concrete to be, what will be my pumping time, what will be my transport time for concrete, all these factor, how close are my reinforcement to each other, and what is the environmental condition, whether it is very hot weather or it is cold weather. All these factors, they can affect the workability demand from concrete. And how we measure workability, either from slump test, compaction factor test, or VB test. And the fifth and the most important point of IS 456 design is the durability requirement. So IS 456, it specifies limits on concrete grade, W by C ratio, and minimum cement content based on exposure condition. So it classifies exposure condition into different categories. There is mild, moderate, severe, very severe, and extreme. Okay, and how are these exposure conditions defined? They are defined based on ability of concrete to resist sulfate attack, corrosion, and freeze and thaw cycle. So you can see in table number 3, there are different set of exposure environment based on the condition. So environment is said to be mild if concrete is protected against all form of aggressive conditions. It is said to be severe when concrete is exposed to severe rain, alternate wetting drying cycles, and occasional freezing and thawing effects. Okay, so based on what environment my concrete it's it will be exposed, I need to select the suitable exposure severity of that environment. Okay, so I will know these conditions which are there in the surrounding, and based on the condition I will determine whether my exposure is mild, moderate, severe, very severe, or extreme. Okay, then there is another table which is table number 4. I will just zoom this table. Okay, so in this table, it specifies the requirement of concrete which is exposed to sulfate attack. Okay, so basically it is based on amount of sulfate which is present in soil and groundwater. So based on the amount of sulfate which is there in soil and groundwater, what type of cement should be used, and what is the minimum cement content that needs to be kept, and maximum water to cement ratio that should be kept, it is mentioned in this table 4. Okay, so this is a very important table 3 and table 4 is very important. It is the first step, or it is like a very important step for uh, checking whether the concrete that we are preparing, it will meet the durability demand also or not. Okay, Then there is this table 5, which is titled as minimum cement content, maximum water to cement ratio, and minimum grade of concrete for different exposure condition. So based on the exposure condition that we arrived from table 3, uh, different limits has been set on water to cement ratio, cement content, and concrete grade for both plain and reinforced concrete. Okay, that you can see in this table. So for example, suppose I am talking about constructing a residential building near seawater shoreline, where concrete is will get exposed to seawater sprays. Since seawater is rich in chlorides, as per my table 3, my structure will come in exposure class very severe. So you can see concrete structure exposed to seawater sprays, it comes in very severe categories. Okay, now for very severe categories and for a reinforced concrete structure, I have limits of minimum cement content 340 kg per meter cube, maximum water to cement ratio of 0.45, and minimum grade of concrete is M35. So this is how during concrete proportioning we use IS 456 to set limits on different design parameters. Okay, and these design parameter limits we need to take care when we do proportioning according to IS 10262. Okay, I hope everyone are clear with the role of IS 456 in mixture design. Any doubt in the IS 456 part? Yes, generally, since mineral admixtures they take time to show their action. For SCMs, we usually check the strength after 56 days. However, most of the codal provisions that you will see, they define 20 days only as characteristic compressive strength, because it is like a baseline for deciding whether the concrete batch that we have prepared is okay or not. But whenever you add SCMs, it is better to check strength at 56 days rather than at 20 days to get a true representation of what quality of concrete you have prepared and what is the strength of the concrete. So I guess there is some code. I don't remember the code number. There's some Indian standard which has mentioned that 56 days is a better indicator for mineral admixture added concrete. And the reason is low strength grain of SCMs. I hope it is clear. When we do experiments in lab, we even go up till 120 days to check long term effect. Okay, but 56 days is a good representation for fly ash or for slag or for silica fume. Okay, so now after IS 456, we have IS 10262. Now, according to IS 10262, the steps of concrete mixture design is as follows. So, step 1 is determining the target mean strength for mixture proportioning. So, to ensure that not more than specific number of specific proportion of test results are likely to fall below characteristic strength, the concrete mixed strength has to be proportion with the higher target compressive mean strength. Okay, so that's why we use this equation. Okay, we want a concrete to have a FCK value. Okay, we know M30, we want to cast M30 grade concrete where 30 is the FCK characteristic compressive strength. But since we want to be on the safer side and we want that 95% of samples should pass this value, we design for a target mean strength which is higher than the characteristic strength of concrete that we desire. Okay, so total number of test strength of samples required to constitute acceptable record of calculation of standard deviation shall not be less than 30 samples. So code says that minimum 30 samples you should cast first to check the value of standard deviation and to get an estimate of target mean strength. Okay, where sufficient results of particular strength grades are not available, the value of standard deviation given in table 1 may be assumed. So suppose you don't know what standard deviation you should take, so code says that if you don't know the standard deviation value that you should take, you should refer to table 1 of IS 410262. Okay, where for different grade of concrete, standard deviation is given, which you need to assume. So suppose I'm casting a M30 grade concrete, then my FCK value is 30 plus 1.65 times standard deviation is 5. Okay, so this will be around 38.5. So my target mean strength, that strength for which I'm designing concrete, should be 38.5 MP. Okay. Now, second step is determining the W by C ratio. So, selecting W by C ratio is based on experience or starting trial for durability criteria. So, either you can go with experience, like what grade of concrete you want and what, as per your experience, what W by C ratio will be suitable, or you can go from durability criteria, like we saw in this table, what minimum, maximum W by C ratio code is saying. Okay, so generally, we have such curves which are present in literature that gives us an idea of how W by C ratio can affect the strength. Okay, so this curve is present in ACI code. Okay, for strength to W by C relation. So suppose I want a concrete of strength M40 grade, then I can have a rough idea of what W by C ratio will work for me. Okay, and then I can check this W by C ratio with my durability condition and validate whether I can go with that value or not. Okay, so now for the same W by C ratio, the compressive strength of concrete can be influenced by several factors like cement type, use of SCM, aggregate gradation, shape, texture, admixture. A lot of things can affect the strength of concrete. It is not just the W by C ratio. Therefore, just relying on W by C ratio to get strength may not be enough. And that's why trial mixture design is done first to verify whether the proportioning is right or not, and if it is not right, then we do the adjustment in proportioning to get the to achieve the desired strength. Okay, so just relying on W by C ratio is not enough. Third step is selection of water content. So, water content used in concrete is influenced by several factors. As we increase the size of aggregate, or as we reduce the W by C ratio, or reduce the slump, or use round aggregates, or use water reducing admixture, I will reduce the water demand that I require from concrete. On the other hand, if there is increased temperature in the surrounding, there is more cement content, there is more requirement of slump from concrete. If we have higher W by C ratio, if we have angular aggregates, or if we have lower proportion of coarse aggregate to fine aggregate, then it will increase the water demand. So water demand from concrete, it may increase or it may decrease based on what we need from concrete and what are the type components that we are using in concrete. So table 2 is there, which gives us the maximum water content per meter cube of concrete based on nominal maximum aggregate size. Okay, so you can see in this table, this nominal maximum size of aggregate is given and maximum water content to be taken is given. Okay, so like suppose I have my nominal maximum aggregate size is 10 mm, then my maximum water content should be 208 kg per meter cube of concrete. Okay, and this value is for coarse angular coarse aggregate and for a slump of 25 to 50 mm. Now there is another clause which is IS clause 9.2, which gives details about how to do correction if we are increasing slump. Okay, so for each 25 mm increase in slump, this value is 25. I need to increase the water content by 3%. Suppose I'm using 208 kg water. Okay, and this is for 50 mm slump. Now suppose I want my concrete to have 100 mm slump at fresh state. So I need to increase this value by 6%. So it will be 208 times 1.06. Okay, so this much water I need to take. Okay, assuming that I have angular core segregate. Okay, so this is for slump increase. Then if we are using different aggregates, so like for subangular aggregates I need to decrease by 10 kg water. If I have gravels plus crushed aggregates, then I decrease water content by 20 kg, and if I have round aggregates I decrease water content by 25 kg, because we know rounded aggregates, they allow proper flowability in concrete, so we can decrease the water content that we are taking in concrete. And then when plasticizers are used for normal range water reducing admixture, which is designated by plasticizer P, the water content can be reduced by 5 to 10%. However, for super plasticizers for high range water reducing admixtures, we can reduce the water content by 10 to 30%. Okay, so based on the composition that we are using in concrete, different criterias are set on water content that we are taking during the initial trial mixture design. Now, till now, we have fixed the target mean strength, we have fixed the water to cement ratio, and we have fixed the water content. Now, fourth step is the calculation of cement content. Okay, so the cement and the supplementary cementitious material per unit volume of concrete may be calculated from free water to cement ratio and the quantity of water used per unit volume of concrete. So we know W by C ratio, and we know, so this value we know the water content, so we can determine the cement content per meter cube of concrete. Now the cementitious material content so calculated should be checked with minimum cement content requirement for durability criteria. Okay, so as we have seen in this table 5, whatever cement content we are getting, we need to check with this value. So suppose for very severe condition we got a cement content of 300 kg per meter cube from IS 10262, but IS 456 code says that minimum cement should be 340 kg per meter cube. So instead of 300, we'll take 340 kg per meter cube cement. Okay, so this is a cross check that we need to do every time. Now, after we know the cement content, the next step is the calculation of total aggregate content. So, for 1 meter cube of concrete, the volume of aggregates that I need will be 1 minus mass of cement or binder divided by specific gravity minus mass of water divided by 100. Okay, so subtracting the volume of cement and volume of water will give me the volume of aggregates that I need to use, okay, per meter cube of concrete. Now we know water, we know cement, and we know the total aggregate content. So next step is going to be into subdivision, that is determining the coarse and the fine aggregate proportion in total aggregate content. So approximate values of these aggregate volume are given in table 3 of IS 10262 for WIC ratio of 0.5. Okay, so you can see based on nominal aggregate size, nominal maximum aggregate size, the volume of coarse aggregate to fine aggregate ratio is given for different zones of fine aggregate. Okay, so when we do characterization of aggregate for fine aggregate based on the particle size distribution, we'll get an idea whether fine aggregate is in zone 4, zone 3, zone 2, or zone 1. And from the gradation of coarse aggregate, we'll get the maximum nominal size of coarse aggregate. Then once we know these two values, we can determine the proportion of coarse aggregate to fine aggregate using this table 3. This table is for water to cement ratio of 0.5. Okay, so we need to suitably adjust the ratio for different W by C ratios. Okay, so how those adjustment comes, it comes by experience and it comes by more trial mixes. Then code says one more thing. For more workable concrete mixes, which is sometimes required when placement is done by pump or when concrete is required to be worked against congested reinforcement steel, it is desired to reduce the estimated coarse content by 10%. Suppose we need to pump concrete for a longer distance, or if there is very congested reinforcement caging where coarse aggregate may hinder or may get blocked between reinforcement. Suppose this is my reinforcement cage inside. Now if I take a coarser aggregate, it may not pass through the gaps between the reinforcement. So in such cases we need to take care of the maximum aggregate size also, and we can decrease the coarse aggregate content by 10%. Okay, that is what code is saying. Okay, once we know the ratio, we can determine the mass of fine aggregate and coarse aggregate. So whatever factor we are getting, 1 minus that factor times the total volume of aggregates will give me the volume of fine aggregate, and mass of fine aggregate will be volume times the specific gravity of fine aggregate. Similarly, we'll get the mass of coarse aggregate. Now within coarse aggregate also, as we discussed in week 3 content, there are multi-sized aggregate. So Step 8 deals with the combination of different coarse aggregate fraction. Okay, so if you see in step 6 in table 3, there is coarse aggregate and it was mentioned nominal aggregate size. So in step 8, to achieve this nominal aggregate size, how we need to proportion different sizes of aggregate in suitable proportion is given. Okay, so if you see the second half of this table, so this is graded aggregate. This is for graded aggregate to belong to a particular nominal aggregate, maximum aggregate size. Like suppose I have 10 mm and 20 mm nominal single sized aggregate. Then if I am using 50-50% combination of both, then for getting 20 mm nominal maximum aggregate size, the value of sieve analysis of this graded aggregate batch will should configure this value that is given here. Okay, so whatever sieve analysis data I will get by doing sieve analysis of 10-20 mm nominal aggregate size, uh, pass, then based on the sieve analysis of that, I will compare the sieve analysis data with this column and I will check whether 50-50% mixing of 10-20 mm aggregate is giving me 20 mm nominal aggregate size or not. If not, then I need to modify my aggregate proportioning. Okay, so this is how we use this table 2 of IS 383 to get the nominal maximum aggregate size. And finally, and most importantly, once all proportioning is done, the last step is the correction of water content based on the moisture content in aggregate. So, mixture design of concreting, it is done assuming that we have saturated surface dry conditions of aggregate. Okay, now what we mean by SSD, what do we mean by saturated surface dry? So it means that when my aggregate is completely saturated with water from inside and it is dry on the surface, so such aggregate they won't absorb any moisture, water from my concrete proportioning. Okay, so those aggregates are known as SSD aggregate, like you can see in this figure here. I will just make that figure a little bigger. Okay, so in this figure, this third image, it represents a SSD aggregate. Okay, so aggregate is completely saturated from inside, so it won't absorb any moisture from my water that I am adding for concreting. Okay, so this is the aggregate that we have assumed till now, till step 8 we have assumed aggregates are in SSD state. However, the aggregate are not always in SSD condition, and often maintaining aggregates in SSD condition before batching and casting is also challenging. So a certain amount of additional water and a certain correction in aggregate content should be added during concreting to account for water absorption capacity for in place aggregate. So the aggregates that I'm actually using, they may not be in SSD condition, they may be in a condition which is between very dry and very saturated. So such aggregates, they will absorb some moisture from the water that we have added for concreting. Now we don't want that the water to cement ratio that we desired, it should get disturbed. So what we do, we add additional water in concrete, which, and that water is for aggregate absorption. Okay, and accordingly we do correction in both aggregate content and water content. Okay, so suppose I have SSD condition aggregate. Now, how to calculate what is the absorption capacity of aggregate and what is the moisture content in current aggregate? So, from SSD weight, if we oven dry this SSD aggregate and we take the difference in between weight of this aggregate and this aggregate, then I will know what is the water absorption capacity of my aggregate. Okay, and from in place aggregate, if I do oven drying, then I will know the moisture content that is there in my aggregate. So extra water, that is the difference between these two, is what I need to add in concrete. Okay, and accordingly I need to do the correction in the aggregate weight also, so that I can convert SSD into in situ. Okay, what is actually there. Okay, so for these two corrections, there are calculations that are mentioned that you can see here. Okay, just give me a second. Okay, so here at the bottom you can see how we do this correction. So dry weight of aggregate is nothing but SSD weight into 1 minus the water absorption capacity of aggregate. So in this way we are removing the water present in the SSD aggregate to get the dry aggregate. And weight of aggregate in current state, which is my intermediate state, will be dry weight times the moisture content that is there in aggregate. How much moisture is there actually in aggregate. So this is how I will get the weight of aggregate in current state. So I knew SSD weight. From SSD weight, we calculated dry weight, and then from dry weight, we calculated the aggregate weight in current state. That is what I'm using during concreting. Now, how to take into account the extra water that is needed? So, total water absorbed by dry aggregate, I know it will be dry weight into W percent, and total additional water will be total absorbed water minus M percent of dry weight. So, it is basically W percent minus M percent. Okay, so this was my dry aggregate. This is my in situ aggregate, the aggregate that I have in reality, and this is my SSD aggregate. Okay, difference between these two is W percent, and this difference between these two is M percent. Okay, so how much extra water I need to add? It will be this much, W percent minus M percent times dry weight of aggregate. Okay, so the same thing is written in this equation. Okay, so in this way I will be able to do the water correction, and I will get my aggregate into in situ condition also. And both of these corrections will ensure that whatever free water I am adding into concrete, it is just for the W by C ratio for workability and strength, and none of that water will be absorbed by aggregate. Okay, so this chart was shown in NPTEL recording, which summarizes the entire thing. We have strength, we have quality control, we have mean strength, type of cement, age required, durability. That helps us to define the W by C ratio. We get the aggregate cement ratio, we get the overall grading of aggregate, proportioning of each fraction. All these things helps us to determine the mixture proportioning. Based on the workability requirement also, and aggregate shape and aggregate size, all these also affects the workability. And finally, once we have the mixture proportioning, based on the capacity of the concrete mixture, I can define the weight of ingredients per batch. Okay, I hope everyone are clear with this IS 10262 design method. If you have any doubt, you can ask, and others just try to answer these three simple questions, theoretical questions, and then we'll see one numerical. What ratio W by C for M30? So basically for this, you need to do some trial mixtures. Okay, or you can see from this W by C ratio relationship with strength. Okay, so for M30, generally we go for a very high W by C ratio between 0.5 to zero point 0.6. Okay, so between zero point 0.5 to zero point 0.6, suppose you choose 0.55, then with that W by C ratio, you need to do one trial casting. Then after 28 days, check the strength of concrete and check whether it is passing the M30 criteria or not. If it is passing the criteria, that means that the whatever W by C ratio you took, it is correct. If it is not correct, then you need to increase or decrease the W by C ratio based on whatever value you got. To prepare a concrete mix of M60, to have any proper ratio this experiment? No, for high strength concrete that is M60 and above, we need to go with past literature. So there are people who would have prepared M60 grade concrete, so we need to check what proportions they have taken, and then we need to repeat those proportions and check whether we are getting the strength or not. Like, it is based on trial mix proportioning. Code doesn't decide the ratios of aggregate cement water for M60 and above grade. All these things, they need to be done by trial proportioning or using literatures present of researchers who have already done the mixture design. Just try to answer question number 7 here now. According to IS 456, which of the following statement regarding mixture proportioning is true? We can't just define what is the mix ratio for a M30 grade or something. For all the mixture proportioning, we need to first categorize the components, like what is the coarse aggregate, what is the fine aggregate, what is the specific gravity of these aggregates, what is the gradation of aggregate, what is my cement, what is the specific gravity of my cement. Then when we know the material properties of all the components that are there, then only we can determine the mixture ratio of those material to get a certain strength. We can't randomly decide, okay, this much w by c ratio, this much cement content will give me the strength. It all depends upon each component that we are using. Can anyone tell me the answer for question number 7? Correct answer for question number 7 will be B. Okay, so mixture design should have lowest possible W by C ratio without sacrificing workability. So this is a statement that is given in IS 456. Okay, so you should take minimum possible W by C ratio to get a particular workability while doing the mixture proportioning. Okay, the higher W by C ratio, it is not desired because it will bring into concern the durability issues. Okay, question number 8. As per IS 10262, the selection of water content is primarily based on which factor? So, water factors determine the selection of free water content. For question number 8, can anyone tell me the answer? Yes, one of the correct option is C. So as we have seen in the tables, maximum nominal aggregate size and workability demand, that is the slump that we need from concrete, that define the free water content. Then exposure condition also is important. So suppose as we saw in IS 456 code, we have limits on W by C ratio that is there based on the exposure condition here as we saw. So whatever water to cement ratio I'm getting, whatever free water content I'm getting and whatever cement content I'm taking, I need to check W by C ratio from these tables also, whether they are justifying the durability condition or not. Okay, so that's why exposure condition can also play a role in selecting the free water content. And slump requirement, durability requirement, it will be the same thing. Question number 9. For a reinforced concrete mix, the slump requirement as per IS 456 in for normal conditions in structural members should be in the range. So for normal beams, columns, in normal condition, like not severe condition or not mild condition, in moderate condition, what is generally the slump requirement from concrete? Yes, the correct answer is 50 to 100 mm. Okay, so for reinforced concrete elements like beams and slabs, a moderate workability of range 50 to 100 mm is suitable. Lower slump values like 20 to 50 mm, it is used for mass concreting like foundations, while higher slump like 100 to 150 mm and more, it is used when we want more flowability in our mix, like heavily reinforced section or when we need to pump concrete. In such cases we go for higher slump, initial slump value. Okay, Now we have a mixture design question that you can see here. So here we need to design a concrete mix for M30 grade concrete to be used for a reinforced concrete structure exposed to severe environmental exposure condition, and the structure requires an initial slump of 100 mm, and it is given following data is given to us. So we know the cement type, it is OPC 43 grade. We know the maximum nominal aggregate size. We know the specific gravity of cement, specific gravity of coarse aggregate, fine aggregate, water absorption capacity of coarse aggregate and fine aggregate. What is the moisture content in situ aggregates that is given to us? It is dry. So whatever aggregates that we have, it is in dry state. We have sand conforming to zone 2 grade. Exposure condition, it is given to us as severe. Degree of supervision is good. Target slump is 100 mm, and standard deviation from site data also it is given to us is 5 mp. Okay, so knowing all this data, just give it a try to start with the mixture proportioning, follow one step at a time and just do some calculation, and just think like how you will do the proportioning. Okay, I will wait for a minute and then I will tell you the answer. Okay, in the meantime, just tell me the steps how you will go along. So can anyone summarize me again what are the steps of mixture proportioning? From where we start and what is the last step? Just think. Okay, let's see the answer. Okay, so step 1 will be determining the target mean strength. Okay, so how we will determine target mean strength? It is nothing but FCK plus 1.65 times standard deviation. So my FCK is 30 plus 1.65 times standard deviation, which is given to me in the question is 5 MPa. So I will take 5. So it will be 38.25 MPa. Okay, so this is my target mean strength for which I need to design concrete. Now step 2 is selection of water to cement ratio. So for this, we can either go with the experience or we can use the durability limits. So suppose I am using IS 456 table 5. Okay, the durability limit table. So I have been given that my structure is in severe exposure condition. So let's see the table number 5. So for severe exposure condition and for reinforced concrete, my maximum free W by C ratio is 0.45. So let's take 0.45 W by C ratio. So either you can go with 0.45 W by C ratio, or you can use the compressive strength versus W by C ratio curve and choose the appropriate W by C ratio. So since it is a trial mixture design, let's take a W by C ratio of 0.45. Okay, so we have fixed W by C ratio. So step 3 now will be selection of free water content. So for this I will use IS 10262 table 2. Okay, so we have 20 mm nominal maximum aggregate size, and target slump which is given to us in question is 100 mm. Okay, now we don't know the aggregate shape. Okay, whether it is round, whether it is angular. So I am assuming angular aggregates. Okay, that is there. Okay, so as per table 5, as you can see here, For angular aggregate and for 50 slump and for nominal maximum aggregate size of 20 my maximum water content is 186. Okay, so this is for 50 slump. Now I want 100 slump, so I will increase this value by 6%, 3% plus 3% for every 25 increase. So my free water content will be 186 times 1.06, so it will be 197 kg per meter cube of concrete. Now since nothing is given about SP dosage, we are not using that in this question. However, you can repeat the same question by assuming some SP dosage also, and suppose you are adding 0.5% SP, then accordingly you can decrease 5 to 10% of water content from this. Okay, and then you can repeat the design. Okay, so this is like we have determined the free water content. Now step 4 is estimating estimation of cement content. Okay, so we know W by C ratio is 0.45 and W is equal to 197 kg. So cement will be equal to 437.7 kg. Okay, 197 divided by 0.45. Now we need to check it from IS 456. So as per IS 456 table 5, which is for durability condition, if we go to that table again, so for severe exposure condition, minimum cement that we need to take is 320 kg per meter cube. And whatever cement we are taking here, it is more than that. Minimum cement required is 320 kg per meter cube, and we have taken more than that. So this value is okay. Okay, so we have determined the cement content now. Now, next step will be step 5, determining the total volume of aggregates. So assuming 1 meter cube concrete is what I am preparing, volume of total aggregates will be equal to 1 minus what is the volume of cement? It is 437.7 divided by specific gravity. So it is 1000 into 3.15 for OPC. Specific gravity is 3.15, so divided by density, minus 192 divided by density of water, which is 1000. Okay, so if when I will do this calculation, it will come out to be 0.669 meter cube. So this is the volume of my coarse aggregate. Now step 6 is proportioning of coarse and fine aggregates. Okay, so for 20 nominal aggregate size and for zone 2 sand that is given to us, we need to go to the table again, which is given in IS code. Okay, so this is 20 aggregate and zone 2 sand. So for this we need to take a coarse to fine aggregate ratio of zero point 0.6, but this is for W by C ratio of zero point 0.5. So you can adjust this value also, or you can take the same value for now, and once you do the trial mixture design and you check the strength of concrete, then later on you can adjust the proportion if needed. Okay, so what is the value? Volume of coarse aggregate is 0.62 times the total volume. So it is 0.62 times 0.669, so that will be 0.415 meter cube. Okay, so mass of coarse aggregate will be volume divided by density, and we have been given the specific gravity of aggregate, so it will be 0.415 times density, so it is 2.7 into 1000. So it is 1120.5 kg. So this is my volume of coarse aggregate, mass of coarse aggregate. Then volume of fine aggregate will be 1 minus 0.62, which is 0.38 times 0.669, so it will be 0.254 meter cube, and mass of fine aggregate will be 0.254 times density of fine aggregate. Density is specific gravity into 1000, 2.6 into 1000, so it will be 660 k.4 kg. So we have determined the volume of coarse aggregate and volume of fine aggregate. We know the volume of cement and we know the volume of water that we need to add per meter cube of concrete. Okay, now step 7, mixing coarse aggregates of different size. So to achieve a nominal maximum aggregate size of 20 mm, we need to have an exact sieve analysis data that is not given in this question right now. Okay, so what we need to do, we need to opt for general practice. Like right now in this question we'll opt for general practice that is used on field. So we may take 50-50% proportion of both 10 mm and 20 mm passing aggregate. That is what we are assuming here, and we are assuming that this will give me, assuming that this will give me 20 mm nominal maximum aggregate size. Okay, so I am assuming this for this question right now. For actual calculation you need to have the sieve analysis data for both 10 and 20 mm single sized aggregate also, so that you can see what percentage combination of these two will give me 20 mm nominal aggregate size. Okay, so that for that we need to do sieve analysis again and again, like for the varying proportion, to check the value that is coming out. Okay, so now we have mass of water, we have mass of cement, we have mass of coarse aggregate. In coarse aggregate also 10 mm, 20 mm percentage we know, and we know the mass of fine aggregate. Now the final step, that is step 8, is the water correction. Okay, now in the question we have been given that the aggregate are in dry state. Okay, so since aggregate are in dry state, then we just need to convert SSD aggregate into dry aggregate, and we need to add water correction for that. Okay, so first, corrected aggregate content will be, to convert SSD aggregate to dry, so it will be, coarse aggregate will be 1120.9 times 1 minus water absorption capacity of coarse aggregate, which is given to us at 0.5%, so it will be 0.005. So this is my dry weight of aggregate. Okay, that is the in situ condition for me right now. And for fine aggregate, it will be the similar calculation, 660.4 SSD weight minus 1 minus water content, that is 0.01. Okay, so these are the dry weight of my aggregate, and since my in situ aggregates are also dry, then this will be the actual aggregate proportion that I need to use in concrete. Now, additional water to be taken to convert these aggregates into SSD will be 1115, which is my dry aggregate content, into the into 0.005 plus 653.8 times 0.01. So this is the total water that these aggregates will absorb, and this I need to add with the free water content that I determined initially. So that was 197. Okay, so this is the total water that I need to take, 209.11 kg. Okay, so this is the total water. Okay, this is the correction in water, and this is the actual water content that we took initially. So this much amount of water I need to add. So from this water, around 12.11 kg of water will be absorbed by coarse aggregate and fine aggregate to convert them from dry to SSD, and the remaining 197 kg it will be used in workability and strength cement hydration. Okay, so for 1 meter cube of concrete, now we know the proportion of all the mixture components. I hope this question is clear. Any doubt in this question, how we proceeded with the questions and how we followed different steps of mixture design? Okay, if there are no doubts, we'll proceed ahead. Now, after IS method, Indian Standard Method, we have DOE method of mixture design of concrete. So, which is a widely used British standard, okay, which is developed in UK for designing the concrete mixes. Okay. Now, what are the benefits of DOE method which makes it widely used? Okay, so these benefits are simple and systematic tables. So this code is simple and systematic as it uses tabulated values and graphical data for easy design. It ensures workability and strength. So it offers balanced water content for both workability and strength, and it is based on experimental data. So whatever tables and graphs that are prepared in DOE method, they are based on extensive research and practical experience. Okay, so that's why they are widely used for concrete mixture designing. So in this slide, I have summarized the entire step procedure for DOE method. So like always, the step one is the target mean strength calculation. Then step two is the selection of water to cement ratio. Okay, for this DOE provides a graph relating strength to W by C ratio. Then step three is selection of free water content. So free water content is determined based on the required workability and maximum aggregate size, for which again DOE provides tables for recommended water content. Then determining the cement content. This ensures that the cement content is above minimum requirement of durability, for which also DOE provides a table. Then determining the total aggregate content, which is based on density of concrete and chosen water content. For this also DOE provides a graph. And finally, determining the ratio of fine and coarse aggregate proportion. So this is selected based on the maximum size of coarse aggregate, for which DOE method provides a table for estimating the proportion. So in next few slides, we'll see each of these steps and how DOE methods define each of these steps. So after selecting the required compressive strength that we demand from concrete, for W by C ratio determination, DOE method provides a table and a corresponding figure. Okay, as you can see on this slide. Okay, so first in table, for a known cement type and coarse aggregate type, we determine the approximate compressive strength that can be made with W by C ratio of zero point 0.5. Then with this strength, we go to the curve and we find where the strength will lie on W by C ratio 5 ratio, and then we'll draw a parallel curve through that, and then from that we'll get the actual W by C ratio that we need to take for the strength that we require. Okay, now this may sound a little confusing here right now, so let's see it by an example. So suppose I want to prepare a M45 grade concrete. Okay, and I have OPC type 1 cement, and I have uncrushed coarse aggregate that is given to me. Okay, so these three things is known to me. Okay, so at 28 days with W by C ratio of zero point 0.5, so if you see this OPC and uncrushed type at 28 days for W by C ratio of zero point 0.5, my strength will be around 40 to 42. So I am assuming my strength is 42 MPa. Okay, with for this grade, for this for this cement, for this W by C ratio. Now I will go on the curve and I will draw a horizontal line, which is passing through 42, and I will draw a vertical line passing through zero point 0.5 W by C ratio, and I will find the point where these two things are interacting, horizontal line and vertical line. Now I will draw a curve parallel to other curves passing through this point, and on this curve, for the desired strength value of M45, I will draw a horizontal line and I will check where it is dropping vertically. Okay, so like this, I will determine what is the W by C ratio I require. So W by C ratio I require for M45, it will be around 0.475 or 0.46. Okay, so what we did, we drew an horizontal line through 42, and we drew a vertical line through W by C ratio of zero point 0.5. We found the interacting point through which we made a curve which is parallel to the above and below curve, and on this curve for M45 grade we checked what is the W by C ratio coming. So this is the method which is presented by British method. Okay, this is the way British method defines the W by C ratio determination. Now next step is determining the free water content. So for this again we have two tables. In the first table we have the maximum aggregate size and the type of aggregate, and for the known value of slump, okay, we can choose the required free water content. Okay, and in the second table we have the reduction factors to free water content when fly ash is used. Okay, so why we are reducing water content when we are increasing the fly ash proportion? Because of ball bearing effect of fly ash. Okay, so for different slump of concrete, for different proportions, the percentage of fly ash added, this table determines how much water content we need to reduce. Okay, so suppose I have a nominal maximum aggregate size of 20 and I have uncrushed aggregate and I want a workability slump of 50 So I will go to this point and I will take a water content of 180 kg per meter cube. Now, if I am using 20% replacement of OPC with fly ash, then I need to decrease the water content by 10 kg. So I will take my water content as 170 kg per meter cube. This is how we read these two tables. Now, after determining W by C ratio and free water, we will determine the cement content, and we will also check it with durability limits like shown in this table, where based on the exposure severity and for known based on the exposure severity, we have the limits on cover, W by C ratio, cement content, and concrete grade. Okay, so for these exposure severity, these are the limits on cover, and these are the limits on W by C ratio that is given to us. Okay, either we can follow this table or we can follow IS 456 table also. Okay, now we determine the total aggregate content. So for this, DOE method provides a curve to calculate the wet density of concrete first. Okay, and how we calculate the wet density of concrete. So for this, we have two values that we need to know. We need to know the specific gravity of aggregate. Okay, and we need to know the free water content that we have calculated. So based on the two things, we will draw a vertical line. We'll see this. Suppose my specific gravity of aggregate is 2.7. So on this curve I will get this interaction point, and then I will draw an horizontal line and I will get the wet density of aggregate. Once wet density of concrete, once I know the wet density of concrete, total aggregate content will be wet density minus mass of cement minus mass of water. And finally, to determine the fine and coarse aggregate proportion, we have different curves that are provided, which are based on W by C ratio, slump requirement, and percentage of fine aggregate passing through 600 micron sieve. Okay. So from using this, we can determine the proportion of fine aggregate. So here you can see there are three groups of curve, and each group has four figure. So this is one group, this is one group, and this is one group. Okay, so this group is for 10 nominal aggregate size, second group is for 20 nominal aggregate size, and third group is for 40 nominal aggregate size. Okay, once we know the nominal aggregate size and we know the slump that we require from concrete, and what is the percentage of fine aggregate passing through 600 micron sieve, which is given here. Okay, and we know the W by C ratio taken, so we'll draw a vertical line from this value, and from this slump we'll get the interaction point, and when we draw horizontal we'll get a value on the y-axis that will be my proportion of fine aggregate. Okay, so out of 100%, suppose 40% is coming out to be fine aggregate, then 60% of the weight will be of coarse aggregate. So this is how DOE method defines the proportion of fine aggregate and coarse aggregate. So we'll see one numerical just to understand the application of all these tables and graphs. In the meantime, if you have any doubt regarding Dewey method or any of the table or figure, you can ask. When we add silica fume, W by C ratio increases. W by C ratio is something that we are fixing. Okay. Generally, what happens when we add silica fume? We know that it will harden very fast. It will reduce the setting time of concrete. It will make concrete very stiff. So that's why we generally add some super plasticizer or some water reducing admixtures which can enhance the workability of concrete. Okay, because silica fume, it will hamper the workability. What is 0.005? In that question, if you see, if you will just go through this question once more, 0.5% was the water absorption capacity of coarse aggregate. So for correcting the weight of aggregate, I multiplied that. 0.005 per 0.5% means 0.005 value in terms of value. Okay, just see this slide once again and do the mixture design on your own, and then check the calculations that I have done. Okay, just think how you will go along with this mixture design, and if you have any doubt regarding Dewey method, just ask now. I will mute myself for a minute, for a couple of minutes, and then we'll see the solution for this question. In the meantime, if you have any doubt, you can post in the message chat box. Okay, let's see the solution for this question now. Okay, so step one is calculating the target mean strength. So it will be FCK 45. So we are desired to cast M for 45 MPa strength we that want. So 45 plus 1.65 standard deviation, which will be 5. Okay, so it will give me a strength of 53.25 MPa. So that is my target mean strength that I want. Okay, now step 2 is W by water to cement ratio estimation. Okay, so for this we'll use the DOE chart. Okay, so it is given to us in the question that we have type 1 cement. Okay, as okay, type 1 cement and uncrushed coarse aggregate. Okay, these two things needs to be mentioned. I will just mention here. Assume type 1 cement and uncrushed coarse aggregate. Okay, so these things we need to mention. Okay, suppose this is mentioned to us, so what we'll do, we'll go to the table that is given to us. Okay, in this table, for type 1 cement uncrushed coarse aggregate at 28 days for W by C ratio of 0.5, the strength is coming out to be 42 MPa. So I will just take this table and I will paste in the new slide. Now in this table, what I will do, at 42 MPa, suppose this is 42 MPa, I will draw a horizontal line and I will draw a vertical line through point 0.5, and I will check whether where they are interacting. They are interacting somewhere here. Okay, now across this point, I will draw a curve. Okay, and now what strength we want? 53.25. So 53.25, suppose it is lying somewhere here. Okay, so for that value, I will get this interaction point, and that interaction point I will drop down. Okay, so this will give me the W by C ratio that I should take for achieving this strength value. Okay, so suppose my W by C ratio required, it is coming out to be 0.42. Okay, so suppose from this method I get W by C ratio of 0.42. Okay, now step 3 will be water content estimation. So we know we have 20 uncrushed aggregates, and question has given that we need a low workability slump, we need of 10 to 30 Okay, so from this table that is given to us, for 10 to 30 and uncrushed 20 aggregate, my free water content required is 160 kg. Okay, so I will take free water content as 160 kg. Now since nothing is mentioned about addition of fly ash, so that third table we can ignore, the second table we can ignore for now. Now we need to check whether this free water content is suitable for exposure condition also or not. Okay, so we have estimated free water content and we know the W by C ratio. Okay, so exposure condition which is given to us is moderate. So for moderate exposure condition, okay, the water to cement ratio that is allowed is 0.5. Okay, so the water to cement ratio that we have taken is lower than 0.5, so it is acceptable, so we can go with that water to cement ratio for now. Okay, now once we have water content and water to cement ratio, step 4 will be determining the cement content. Okay, so it will be 160 divided by 0.42, so it will come out to be 381 kg. Okay, again we can check with the durability criteria and it will come out to be 300 kg per meter cube will be the minimum requirement, so this 380 kg will be acceptable. Step 5 will be determining total aggregate content. Okay, so I have free water of 160 kg and specific gravity of aggregate, it is given to me as 2.65. So I will paste that table here, this figure. Now in this figure, 2.65 will lie somewhere in between 2.6 and 2.7. So I will draw one line for 2.65 like this. And I have free water content of 160. So this will be my line here. So interaction point will be somewhere here and it will come out to be somewhere in between these two things. So I will take average of 2400 and 2500. So 2450 suppose I will consider. Okay, so my wet density of concrete is 2450. So my total aggregate weight will be 2450 minus weight of cement 381 minus weight of water 160, so it will be 1909 kg. So this is my total aggregate content. Okay, now next step is determining the fine and coarse aggregate proportion. Okay, last step, step 6 is determining fine and coarse aggregate proportion. Okay, so for this, what all things I know: 20 mm nominal aggregate size, W by C ratio is 0.42, and there is one more data given to us: aggregate passing through 600 micron sieve is 60%. Okay, 60% it is given to us. Okay, now since this is and slump required is in the range of 10 to 30 mm. So these all things we know now. Okay, so since it is 20 mm nominal aggregate size, so I will use this set of curve. Okay, so I will place this curve. Okay, in the second curve for this range, and for 60% this curve. Okay, and for W by C ratio of 0.42, it will be somewhere here. I will get this interaction point, and it will come down as here between 20 to 30. So it is very close to 30, you can see. So I will take 30% as fine aggregate. Okay, so whatever total weight I have, out of that fine aggregate will be 30%. So zero point 0.3 times 1909 will be my fine aggregate. So it will be 572.7 kg, and remaining will be my coarse aggregate, zero point 0.7 times 1909. So that is 1336 kg. Okay, so this is how we do mixture design following DOE method, using the standard figures, tables, and curves that is given to us in the code. Okay, now there can be more corrections also, like SSD correction and all. Those steps will be the same of how we did for using the IS method. Okay, so that's why I'm not repeating those steps here. I hope everyone are clear with this DOE method design. So this is all for today. We discussed IS code method for mixture design, and we discussed DOE method for mixture design. And before that, we discussed an overview of mixture design, focusing on components of mixture design and how they are related to desired properties of concrete. Thank you. Now, if anyone has any doubt regarding the entire session, they can share their